Hi, in this video today we're going to be looking at the last thing that we want to talk about with matrices, and that is transformation matrices. So using matrices to transform objects, rotating them, enlarging them, shearing them, and the matrices that you need so that you can perform those transformations. So this is really cool. The syllabus says we've got to examine the properties of 2 by 2 matrices as linear transformations in the plane, including rotations, reflections, dilations, and shears parallel to the coordinate axes. So we're going through that, the matrices that cause those things to happen. Use matrix multiplication to determine the combined effect of 2 linear transformations. So for example, a rotation followed by an enlargement, and what would the matrix be that causes that to happen? Just the one matrix. And establish and apply the relationship between the determinant and areas of shapes before and after transformation. Okay, so let's go through the basic idea of how we can take a shape and transform it with a matrix. So in this example here, we're going to transform this triangle using the transformation matrix 1, 0, 0, 1. So the way that we do that is that we write the vertices of the triangle in a matrix. So the vertices A is 1, 1, B is 3, 1, C is 3, 2. So we write them in a matrix that looks like this. So it doesn't matter how many points that you've got here, you can write them in a big long matrix. So if you had an octagon, you could have a 2 by 8 matrix going on there. And the way that we use matrices to transform that shape is we pre-multiply by the matrix, the transformation matrix. So we take that transformation matrix, multiply it by the matrix which represents the vertices of the shape, and we get a new matrix. Now that matrix, that new matrix, represents the vertices of the newly transformed shape. So this was point A, this is point B, and this is point C. Notice we go X and Y. This is the coordinates of A dash, B dash, and C dash. You've got to make sure that the order is correct. So using that matrix, we get this new shape where A used to be at 1, 1, is now at negative 1, 1. C is now at negative 3, sorry, B is at negative 3, 1, and C is now at negative 3, 2. So here's what that looks like. Now, clearly you can see, looking at the graph, that what we've done is a reflection in the y-axis. And the neat thing about matrices is that matrix that we had at the start, this one here, always represents a reflection in the y-axis. It doesn't matter what shape you start with, that matrix, when you apply it to the shapes, will represent a reflection. And you can see why that works. For example, in the top one here, you can see that the x values are going to be just times by negative 1. So all the x values are going to become negative. So if they're positive, they become negative. And for the bottom row, we've got 0 and 1 here. So we're just going to have the same y values that we had before. So that's how it works. So that is a reflection in the y-axis. And that's really great if you're using a computer. If you want to perform these transformations, the easiest way to do it is to use these matrices to actually perform those transformations. Here's another example. We've got a quadrilateral this time, and we want to transform it using this matrix here. So here's the multiplication. So we pre-multiply, we write out the points A, B, C, and D in order, and perform the matrix multiplication, and there is our transformed shape. We can then draw the transformed shape on a grid, and here it is here, and we can see what transformation is it that we've undergone there. So it's pretty clear in this case here that it's a rotation. That's the first thing we need to say, it's a rotation. The angle of rotation is 90 degrees, and the center, it's 90, sorry, you should say 90 degrees anti-clockwise. And last thing we need to say is the center of that rotation, and here the center is 0, 0. So if you're asked to describe a rotation, you need to give 3 things: rotation, the center of the rotation, and the angle and direction of the rotation. Okay. So you'll find that all of these ones that we're doing here, the basic ones, all centered at 0, 0, and the reflections are in the y-axis or the x-axis as well, so it makes it a lot easier. Okay, and there's the conclusion about what it is. Okay, so we've got these 3 points here, they're transformed to that by that matrix. Find the coordinates of A dash, B dash, C dash. So have a go at that question there. Okay, looking at example 2 here, by considering the effect on that rectangle, determine the transformation represented by that matrix. I'd like to show you a different way also of finding out what the transformation is just given the matrix. I don't know these off by heart, but I can know a way to work them out each time. So I'm going to show you the way that you can work them out each time. All right, so let's firstly do the matrix multiplication. So we've got 0, 1, negative 1, 0. And we're multiplying it by O, A, B, and C. Okay. So in order, we're going to get across the top time there. It's just 0 times the top ones, 1 times the bottom ones. So it's just going to be 0, 0, 1, 1 along the top. And the bottom line here is just going to be negative 1 times the top line. So 0, negative 2, negative 2, and 0. Okay, the long way here would be actually to draw the shape out. 0, 0, 2, 0, 2, 1, and 0, 1. There's our original shape. It's good to label it as well. So O, A, B, C. And O is staying where it is, so that's in the same place. You can see this is A dash, O dash, A dash, B dash, and C dash. All right. So A has moved to 0 minus 2, which is down here. B has moved to 1 minus 2. 1 minus 2, which is down here, that's B dash. This is 2 here. And C has moved to 1, 0, which is here. So here's our transformed rectangle. This is not to scale, but hopefully you can see that we've undergone a rotation, that this thing here has rotated around 90 degrees, about a center point of 0, 0, and in this case it's 90 degrees clockwise. So that's what that matrix represents. So that's one way of doing it, is actually drawing it out, having a look at the transformation, going, that's what it is. Here's I think a little bit of a better way of doing that. So the matrix here is 0, 1, negative 1, 0. Okay, 0, 1, negative 1, 0. All we need to do to work out what that is consider what's happened to our, what I call kind of the unit vectors in 2 dimensions. Could think of them as points, okay? So think of the point 1, 0 and the point 0, 1. So start with your identity matrix, which looks like this. So think of the point here as 1, 0, and this point here is 0, 1. So just consider what's happened to those points. See if you can work out, just looking at those two, what this matrix has done here. So this one here, we've gone to 0, minus 1, and 1, 0. So a different color here. So the first point, 1, 0, has gone to 0, minus 1. So this point here has gone down to here. Yep. And the other point, 0, 1, has gone to 1, 0. So this point here has gone to here. I can see from that, even just looking at those two, I can see that we've undergone a rotation of 90 degrees. If you want to convince yourself, you could include originally the point 1, 1 also. Okay, so you've got what's called a unit square, and you can look at what goes on with the unit square, and then it's easy to see. Okay, so the unit square, we would end up with something that would be like this. And if you get the numbering right, you can see that we've got a rotation there of 90 degrees clockwise. Okay, next example. We've got a triangle. It's transformed to another triangle by that matrix there. Now this one's a bit tricky. I don't know what this does. 3, 1, 1, 1. We've given that the coordinates of the transformed matrix are these ones here. And we need to find, respectively, we need to find what the original coordinates, A, B, C, are. Then it starts talking to us about the area. So I want to talk about that as well, the area in this question here. Okay, so what we've done in this one is we've said T, our matrix T, 3, 1, 1, 1. We've multiplied it by the 2 by 3 matrix that represents A, B, and C. And when we've done that, we've ended up with this matrix: 22, 10, negative 3, negative 5, negative 13, negative 5. Okay, this is A dash, B dash, and C dash. Okay, what we want to work out is the coordinates of the original matrix. Now, I know you know about how to solve matrices like this. So if we have T times X equals B, let's call it, then you know that to find X, you've got to go the inverse of T times B. And that's the technique I'm going to use to find that original matrix. So I'm going to pre-multiply by the inverse of the matrix T. So let's first write that down. The inverse of matrix T is 1 over the determinant. So the determinant is 3 times 1 minus 1, which is 2. We swap the 3 and the 1 and change the sign of the 2 on the other diagonals. So that is the inverse of matrix T. So let's do the calculation now. Our original matrix is going to be, I'll just call it X in the previous one, it's going to be a half, 1 minus 1, negative 1, 3, times by 22, 10, negative 3, negative 5, negative 13, negative 5. Again, you could multiply the half by this matrix here and then multiply that, or probably easier is just multiply these two matrices together and then times the whole thing by half. Okay? That represents the original points. So A is 6, 4, B is 1, negative 6, and C is negative 4, negative 1. Okay, so the question then says the area of our transformed triangle is 75, and we want to know the area of the original triangle. I guess one way is you could draw this triangle out and start using some trigonometry. We've got the coordinates of the points, so we could do that. There's an easier way though. The area of a transformed shape is determined by the determinant of the transformation matrix. So if the determinant of the transformation matrix is 2, the area of the transformed shape is doubled. If the determinant of the transforming matrix is 4, the area of the transformed shape is 4 times bigger. It's the determinant that tells us how much bigger the area is. Okay? So in this case, our transformed matrix was, let's go back, 3, 1, 1, 1. We know that the determinant of that matrix there is 3 minus 1, which is 2. Therefore, I know when we went from A, B, C to A dash, B dash, C dash, I know that we doubled the area. So if the area of my final shape is 75 units squared, then the area of my original triangle was half that, or 37.5. So the area of triangle ABC is 37.5 units squared.